Hello again, it's Lecturer Joe. We're going to take a look at why three-phase power is preferable to single-phase or multi-phases beyond three. Okay, this is Bob. Bob wants to send his electrical power from over on the left here where he has his supply over to the right where there is some sort of electrical load. So let's suppose Bob wants to send over here 120 kilowatts of electrical power at 400 volts. Well, the cable that Bob uses here is going to have some amount of resistance, so we're going to assume that the resistance of that cable is 0.2 ohms. Same here. Now on a single phase system, the power is equal to the voltage times the current. So over here we want to transmit 120 kilowatts at 400 volts. So the current there is going to be 300 amps. So this current here flowing in this cable, 300 amps. So a current of 300 amps across a 400 volt supply here is giving us our 120 kilowatts of power. However, there's also going to be a voltage drop in this supply cable, and with a resistance of 0.2 of an ohm and a current of 300 amps, there's going to be a voltage drop from end to end of I times R, 300 times 0.2, 60 volts. There's going to be a similar voltage drop in the return cable here of 60 volts, which means that Bob here needs to set his supply not at 400 but at 520 volts. And since he's going to be pumping out 300 amps of current, the total amount of power that Bob needs to put into the system then is 156,000 watts or 156 kilowatts. So at the supply end, Bob's pumping out 156 kilowatts. At the load end here, the customer's getting 120 kilowatts, which is what they need. 400 volt supply, 300 amps flowing. And the missing 36 kilowatts here is due to the losses in this cable and this cable. Now, Bob's happy enough with this deal. He knows he's pumping out 156 kilowatts of power. He knows the customer's getting 120, and he accepts that there's a loss in the transmission system here, 36 kilowatts in total. Bob then heads down to the pub and he gets talking to his mate Dave. And Dave suggests to Bob that he should actually have created a three-phase system, not a two-phase system. So in order to explain what he means, Dave draws out on a beer mat what a three-phase transmission system would look like. And he explains to Bob that this would save him some power. In order to deliver 120 kilowatts to this end, he wouldn't need to pump in 156 here because this is inherently a more efficient system. Now, Bob smells a rat right away and spots that Dave's using 3 cables, not 2 cables, to transmit his power. So he objects to this and says, well, this is bound to be a more efficient system because it costs more to produce. It costs 50% more to have 3 cables than to have 2 cables. Dave's already thought of this, but because Bob is using a cable, let's say, which is this size, which has a resistance of 0.2 ohms, but Dave is using 3 cables that are slightly smaller, such that the total amount of copper in both systems is the same. So that being the case, Dave's wires here, Dave's transmission cables, if you like, aren't 0.2 ohm, they're smaller cables, so they have a resistance of 0.3 ohms, a higher resistance because it's a smaller cable. So Dave has done away with Bob's first objection, which is that being a 3-wire system, this is going to be more expensive to put into place because it actually just uses the same amount of copper. So let's see how the sums work out now. Well, over on this side we still need to deliver 120 kilowatts. It's now being delivered over 3 loads rather than a single load. So that's 3 times 40 kilowatt. So each of these is dissipating 40 kilowatt. On this system, the single load dissipates the whole 120 kilowatt. Now, since there's still 400 volts here and 40,000 watts being dissipated, that means that the current flow here must be 100 amps. And similarly, there'll be 100 amps flowing through this load and 100 amps flowing through this load. Now, Dave knows a thing or two about three-phase systems, and he knows that that does not mean that there's 100 amps flowing here. He knows that the flow here is going to be 173 amps. This current times the square root of 3. So 173 amps in each of these 3 lines. So let's compare the systems at the minute. We've got the same power being dissipated at each side. On this side we've got a single load of 120 kilowatts. On this side we've got 3 loads of 40 kilowatts each. Here there's 300 amps flowing through the load. Here there's 100 amps flowing through each of the 3 loads. Here there's 300 amps flowing in the supply line. Here there's only 173 flowing in each of the 3 supply lines. Now in Bob's system here, there was a voltage drop along the supply of 60 volts, I times R. And here there's going to be a similar voltage drop, I times R. Here it's going to be 173 times 0.3, which is 52 volts. So at the minute, these two systems look fairly similar in the sense that they're both delivering 120 kilowatts. Okay, we've got 60 volts being dropped in the supply line here and 52 here, not that much of a difference. However, here the actual current flowing in the line is a lot lower than in the single phase system, and it's the implication of that that's important. So let's look at how much power is lost in the supply line itself. And the power being lost in these supply cables is I squared R. So here it's 300 squared times 0.2. 300 squared times 0.2 is 18,000. So in this system we lose 18 kilowatts in each of the 2 supply lines. So 36 kilowatts lost. And that tallies here, as we said before, with the fact that Bob's having to put in 156 kilowatts. He loses 36 in the transmission. There's 120 at the far end. In the 3-phase system, we still have losses of I squared R, but I is considerably lower. So 173 squared times 0.3 gives us around about 9 kilowatts in each of the 3 lines, which is 27 kilowatts of losses. So Dave, in order to get 120 kilowatts to the far side, needs to put in 147 kilowatts. Hence the reason why Dave was on the ball. 3-phase is the way to do it. We've got the same amount of copper being used in both systems. 2 wires at 0.2 ohms or 3 wires at 0.3 ohms. However, this system is inherently more efficient.